Hey guys, today in this video we will be learning about what is the derivative and using the power rule. So before we talk about the derivative and all that, we need to first talk about slope. So let's use this linear function as our example. So we can find the slope of this linear function by using the slope formula and 2 points. So here we can see, remembering that slope is rise over run, we can see using the points that the slope of the line here is 1. So in addition to finding the slope, we know that this line has the point 1, 1, which we can then use to find the line's equation using the point slope formula, which I am doing right here. So this line that we have here is actually kind of a special function because we can find the slope of the line at any given point on the line. So for example, if I want to find the slope at that given point, we know the slope there is 1 because this line has a constant slope throughout. However, not all functions have a constant slope throughout. So for example, if I was to draw a parabola, this would be a whole different story. So for this parabola, if we wanted to find the slope at any given point, we would not be able to use the previous method because the parabola does not have a constant slope throughout. So in order to find the slope at any given point here, we would need to use the derivative. Before I get into that though, I want to explain how we can use a secant line to estimate the slope of a point on this parabola. By drawing a secant line through 2 points on this parabola and finding the slope of that secant line, we will have a rough estimate of the slope at any given point between the 2 secant line points. However, this estimate or this slope that we would find would not be exact, and that is why we need the derivative. So something that it's important to know the difference between is a secant line and a tangent line. Now, the most important thing to know about the secant line is that it passes through 2 points on the graph. It is the average slope between those 2 points, and it's an estimate of the slope at a point in between those 2 points. Now, what happens if we move those 2 points on our secant line closer together? Well, it would make the estimate of the slope of a point between those 2 points more accurate because the points would be closer together. Now, if we move those 2 secant line points infinitely close together, they almost become 1 point. That brings me to the definition of a tangent line. What you basically need to know is that a tangent line passes through 1 point on the graph. And the slope of that tangent line is also the slope of that graph at that 1 point. So what I am demonstrating in this drawing here is that if we draw a graph and draw a tangent line at every single point of that graph, that just shows that each point on the graph has its own tangent line and its own slope. So if we graphed every single one of those slopes as its own individual point, we would have obviously a graph, and that graph would have an equation, and that equation would be the derivative. So here is the definition of the derivative, and it is the slope at a given point. Now, the derivative can be both a number if it's at a specific x value, or it can be a general equation that you can plug x values into and get a number out telling you the slope at that x value. So for example, this function that I'm writing down here, 3x squared, could be the equation of a derivative of a certain function. So if I wanted to know what the derivative at the x value x equals 1 would be, I would just plug in x equals 1 into that point and I would get y equals 3, meaning the derivative at x equals 1 of that function would be 3. So now let's talk about how to actually find the derivative from a function using the power rule. Before I begin, I just want to reiterate that the derivative can both be a number or an equation. Now, the scenario in which we would have the derivative come out to be a number is if we had the derivative as a function and plugged in a specific x value into the function to find a specific slope at a specific point on our original function. Now, our derivative can also be an equation. This would happen if we took all the x values, found the slopes at those x values of the original function or the slopes of the tangent lines, and graphed those points as a coordinate. We would come up with a graph, and that graph would of course have an equation. So here I am writing that the equation would happen if we graphed the slope of each tangent line and found its equation, because I feel like that's an easier way to remember, at least for me. Now we can finally talk about using the power rule to find the derivative. Now the power rule usually comes into play with polynomial functions, and that is how we can find the derivative equation of that polynomial. So now let me teach you the power rule on a very simple equation, like y equals x cubed, just a simple polynomial. So our mantra for this rule is bring down the exponent and subtract 1 from the exponent. So what we're going to do here is bring down the 3 to become the coefficient and subtract 1. So this would give us 3x squared as the derivative of x cubed. This can be denoted by y prime equals, and then we write our derivative. So once again, now that we have our derivative equation, we could plug any x value into that to get the slope at that x value. So now we are going to try this out with a polynomial that has more than one term, 2x squared plus 5x. We are simply going to apply the power rule to each term in the polynomial, starting with 2x squared. Now, if we differentiate 2x squared, we are going to get 4x, as we use our mantra of bring the power of 2 down and subtract 1 from the power. Next, we will do the same to 5x, which has an imaginary power of 1. So we're going to bring that 1 down and multiply it by the current coefficient, and then subtract 1 from 1, which becomes 0. And x to the power of 0, as we know, is 1. So our derivative would just be 5. Now, if we had more terms in this polynomial, we would continue, but as we don't, our derivative comes out to be y prime equals 4x plus 5. Here I'm going to write out me taking the derivative of a longer polynomial, and then I will explain what to do when we run into a little bit of a problem at the end. So as you can see, I'm continuing the power rule. So I'm bringing down the 5, multiplying it by the current coefficient, and subtracting 1 to get 15x to the 4th. Next, I'm doing the same with the next term, 2x squared, to get me plus 4x. Next, I'm doing the same with 5x, and which brings me to plus 5. Now we are at 7, and let's think about what it would mean to take the derivative of 7. So because we know that the derivative is the slope at a given point, we are essentially finding a formula to give us the slope at any given point on the line y equals 7. So I'm just going to sketch it up above so we can make sense of this explanation. So because y equals 7 is a horizontal line, we know that the slope of a horizontal line is 0, meaning the derivative of 7 would be 0, which leaves our derivative to be as it is written. This is an important rule to remember, and it's called the constant rule. The derivative of a constant is always 0. So that is all for today's introduction to derivatives and the power rule. I hope you guys enjoyed this video and I hope it was helpful. Please like and subscribe and comment down below if there's any other Calculus AB topics you'd like me to discuss. Bye!